Hello everyone, welcome to session 5 presentation of Unit 3 Registers and Counters. In this session, we discuss about ring counter and Johnson counter. Revision. In session 4, we considered the concept of universal shift register and we discussed about some shift register ICs and their features. The table of contents for this session include realization of ring counter, realization of Johnson counter, and finally we answer some multiple choice questions. Realization of ring counter. The ring counter is constructed using the serial in serial out shift register. In order to convert the serial in serial out shift register into a ring counter, Q output of last flip flop will be connected to the D input of the first flip flop. In the normal operation of the ring counter, the output of the first flip-flop will be set and the output of all the remaining flip-flops are reset. The default state of the ring counter is nothing but the output of the first flip-flop set and the output of the remaining flip-flops reset. For example, if we have 4-bit ring counter, then the default state of the 4-bit ring counter is 1000. It means that the output of the first flip-flop is set to binary 1 and the output of the remaining 3 flip-flops are reset. After creating the default state for the ring counter, Q output of the last flip-flop will be connected to the data input of the first flip-flop. When the clock pulses are applied, the logic 1 output present at the output of the first flip-flop will be shifted to the output of the second flip-flop and the output of the first flip-flop will be reset. When the next clock pulse is applied, the output of the third flip-flop will be set. In this way, the logic 1 output starts to rotate around the ring counter on application of the clock pulses. The stage of the ring counter is nothing but the number of flip-flops used to construct the ring counter. An n stage ring counter has n flip-flops and it produces n different output states. For example, a 4-stage ring counter has 4 flip-flops and it produces 4 different output states. The output state generated by the ring counter directly indicate the decimal count of the clock pulses. Hence, in a ring counter, the decoding is not required for decimal conversion. Realization of simple 4-bit ring counter. Figure 3.13 shows a 4-bit ring counter constructed using 4-bit serial in serial out shift register. The 4-bit serial in serial out shift register is converted into a ring counter by connecting the Q output of the last flip-flop to the data input of the first flip-flop. In order to understand the operation of this 4-bit ring counter, initially the outputs of all the flip-flops are cleared so that the outputs Q3, Q2, Q1 and Q0 are all set to binary 0. Before applying the first clock pulse, the binary value logic 1 is connected to the data input of the first flip-flop and the first clock pulse is applied. After the first clock pulse, the output of the first flip-flop, that is Q3, is set and the outputs of the remaining flip-flops, that is Q2, Q1 and Q0, are still in reset condition. Hence, after the first clock pulse, the output state of the ring counter is 1000. This state is the default state of the 4-bit ring counter. After setting the output of the first flip-flop, the output of the last flip-flop, that is Q0, is connected to the data input of the first flip-flop. After this, the second clock pulse is applied. When the second clock pulse is applied, The binary 0 present at the input of the first flip-flop is shifted to the output of the first flip-flop. The binary 1 present at the input of second flip-flop will be shifted to the output of the second flip-flop. Hence, the output Q2 is now set. When the third clock pulse is applied, the output Q1 will be set, and when the fourth clock pulse is applied, the output Q0 will be set. In this way, the binary 1 value started to rotate from the output of one flip-flop to the output of the next flip-flop. When the fifth clock pulse is applied, the binary 1 output present at the output of the last flip-flop will be shifted to the output of the first flip-flop, and the output Q3 becomes 1. In this way, in a 4-bit ring counter, after every 4 clock pulses, the same output state will be exhibited by the ring counter. Hence, after the 5th clock pulse, the output of the ring counter is Q3 equal to 1, Q2 equal to 0, Q1 equal to 0, and Q0 equal to 0. This is the same output state which was produced after applying the first clock pulse. Hence, in a 4-bit ring counter, the same output state will be repeated for every 4 clock pulses. And also from the function table, we observe that there are 4 different output states that are generated using the 4-bit ring counter. In general, if we have n-bit ring counter, then we can generate n different output states, and also the output states start to repeat after every n clock pulses. The merits of the ring counter is that here we do not require the decoding because the output generated by the ring counter directly indicates the decimal count value. The demerit of the ring counter is that in order to realize a divide by n counter, we should have n flip-flops. And also, in a 4-bit ring counter, only 4 of the 15 different output states will be generated and utilized. Ring counter finds applications in decimal counter, divide by n counter implementation, frequency counters, analog to digital converters, digital clocks, and frequency divider circuits. Realization of Johnson counter. Similar to ring counter, the Johnson counter is also constructed using the serial in serial out shift register. In this Johnson counter, inverted output of the last flip-flop, that is the Q bar output of the last flip-flop, will be connected to the data input of the first flip-flop. And for the remaining intermediate flip-flops, the Q output of the intermediate stage flip-flop will be connected to the data input of the next flip-flop. In a Johnson counter, the output state represented as all zeros represent the default state of the Johnson counter. For example, if we have a 4-bit Johnson counter, the default state of the Johnson counter will be 4 zeros, that is 0, 0, 0, 0. Using an n-stage Johnson counter, we can produce 2n different output states. Figure 3.14 shows the 4-bit Johnson counter. Here the Johnson counter is constructed using a 4-bit serial in serial out shift register, but to convert the 4-bit serial in serial out shift register into Johnson counter, Q bar output, that is inverted output of the last flip-flop, is connected to the data input of the first flip-flop. In order to understand the operation of 4-bit Johnson counter, initially all the flip-flops are cleared so that the outputs QA, QB, QC and QD are all reset to binary 0. Here we observe that the output QD is reset to 0. The inverted output of the last flip-flop, that is QD bar, is binary 1. This value is connected to the input of the first flip-flop before applying the first clock pulse. When the first clock pulse is applied, output of the first flip-flop, that is QA, is now set, and the outputs of the remaining flip-flops, that is QB, QC, and QD, are still reset, but the output QD bar is now set. This is again connected back to the data input of the first flip-flop. When the second clock pulse is applied, this binary 1 will be shifted to the output of the first flip-flop, making the QA output equal to binary 1. And the binary 1 value present at the input of the second flip-flop will be shifted to the output of the second flip-flop, making QB equal to 1. And the outputs QC and QD are still 0. The output QD bar is again set, and this is connected back to the data input of the first flip-flop. When the third clock pulse is applied, output of first flip-flop will be set, the output of the second flip-flop will be set, and the output of the third flip-flop will be set, and the output of fourth flip-flop is still reset, but the output QD bar is again set, and it is connected back to the data input of the first flip-flop. When the fourth clock pulse is applied, the outputs of all the four flip-flops will be set. Hence, QA equal to QB equal to QC equal to QD equal to binary 1. Now we have QD equal to binary 1 and QD bar will be equal to binary 0. This binary 0 is fed back to the data input of the first flip-flop. When the fifth clock pulse is applied, the binary 0 present at the input of the first flip-flop will be shifted to the output. Hence, the output QA now becomes binary 0, and the outputs of the remaining flip-flops will be set. Here we observe that the output QD is set, but the output QD bar is reset to binary 0. This is fed back to the data input of the first flip-flop. When the sixth clock pulse is applied, the binary 0 present at the input of the first flip-flop will be shifted to the output, and the output of the second flip-flop is also reset. The output of the third flip-flop and the output of the fourth flip-flop are set. Hence, the output QD is set, but the output QD bar is reset. This binary 0 present at QD bar output is fed back to the data input of the first flip-flop. When the seventh clock pulse is applied, the binary 0 will be shifted to the output of the first flip-flop, and also the output of the second flip-flop and the output of the third flip-flop are reset to binary 0. The output of the fourth flip-flop, that is QD, is set, and the output QD bar is reset. This binary 0 will be connected to the data input of the first flip-flop. When the eighth clock pulse is applied, this binary 0 present at the input of the first flip-flop will be shifted to the output of the first flip-flop. Hence, the output QA now becomes binary 0, and also the outputs QB, QC, and QD are reset. Hence, after the eighth clock pulse, the state of the Johnson counter will be QA equal to 0, QB equal to 0, QC equal to 0, and QD equal to 0. From this function table, we observe that after 8 clock pulses, the same output state will be repeated. And also, we observe that there are 8 different output states generated by the 4-bit Johnson counter. In general, if we have an n-bit Johnson counter, then we can generate 2n different output states, and the output state start to repeat for every 2n clock pulses. Now let us answer some multiple choice questions. First question: what is a recirculating register? Options are: A. Serial out connected to serial in. B. All Q outputs connected together. C. A register that can be used over again. D. Parallel out connected to parallel in. Here recirculating register is nothing but a ring counter in which the serial output is connected to the serial input pin of the flip-flop. Hence the answer for this question is A, serial out connected to serial in. Second, in a 4-bit Johnson counter sequence, there are a total of how many states or bit patterns? Options are A 1, B 3, C 4, D 8. Using an n-bit Johnson counter, we can generate 2n different output sequences. Hence, if we have 4-bit Johnson counter, then we can generate 2 into 4, that is 8 different output sequences. The answer for this question is D, 8 different output states. Third question, if a 10-bit ring counter has an initial state 1101, 000000, what is the state after the second clock pulse? Options are 1101, 000000, B 0011010000, C 1100000000, D 0000000000. Here we have 10-bit ring counter and the initial state of the ring counter is 1101000000. After the two clock pulses, the two LSB bits are shifted to the MSB bit positions. Hence, after two clock pulses, the state of the 10-bit ring counter will be 0011010000. The answer for this question is B 0011010000. Fourth question, ring counter and Johnson counters are, options are A, synchronous counters, B, asynchronous counters, C, true binary counters, D, synchronous and true binary counters. We know that the ring counter and Johnson counters are the synchronous counters. The answer for this question is A, synchronous counters. Fifth question, what is the preset condition for a ring shift counter? Options are A, all flip-flops are set to 1, B, all flip-flops cleared to 0, C, a single 0, the rest 1, D, a single 1, the rest 0. In a ring counter, the preset condition is nothing but the output of the first flip-flop set to binary 1 and the output of the remaining flip-flops set to binary 0. The answer for this question is D, a single 1, the rest 0. Sixth question, the number of output states or bit patterns produced by a 5-bit ring counter is, options are A 1, B 3, C 5, D 8. Here we have 5-bit ring counter and this ring counter can generate 5 different output states. Hence the answer for this question is C 5 output states. Seventh, the default state of a 3-bit Johnson counter is, options are A 001, B 000, C 111, D 011. The default state of the 3-bit Johnson counter is all zeros, that is 3 zeros. Hence the answer for this question is B 000. Eighth, a 5-bit Johnson counter is initially cleared. The state of the counter after 2 clock pulses is, options are A 10001, B 11100, C 11000, D 00111. In a 5-bit Johnson counter, which is initially cleared, the output generated after the two clock pulses will be 11000. Hence, the answer for this question is 11000. This completes session 5 presentation of Unit 3 registers and counters. Thank you everyone.